All right, let's do something kind of crazy. Let's imagine we're taking a trip, but it's a one-way ticket. We're going on a journey into the absolute darkest, most mind-bending object in the entire universe. Yep, we're falling into a black hole.
So, what would you actually see, if you really fell into one? Let's push all the Hollywood special effects aside for a second. We're going to look at what the real physics, we're talking Einstein's general relativity here, says would go down. So, let's dive in.
Okay, so first things first. You might think the danger starts at the black hole itself, right? Nope. Just getting close is probably the most treacherous part of this whole adventure. The real chaos begins way, way before you get anywhere near that famous point of no return. You're not just floating through empty space. No, you're flying into what's basically an astrophysical gauntlet. See, most black holes aren't just sitting there quietly. They're mess eaters. They're surrounded by this thing called an accretion disk, a giant swirling platter of gas and stars being torn apart. The gravity and friction here heat this thing up to millions of degrees. You'd be cooked by a blast of X-rays and gamma rays. And that's not all. You've got these insane particle winds, way worse than any solar storm. And if the black hole is spinning, it can shoot out these jets of plasma at over 99% the speed of light. Even the starlight around you gets all weird and warped, squeezed into this blindingly bright cone right in front of you. Seriously, you have to survive a cosmic furnace before you can even start worrying about the gravity. So, this brings up a really important point. You've got to pick your black hole carefully. It's not a one-size-fits-all kind of trip. On one hand, you've got your stellar mass black holes. These are, maybe 10 times the mass of our sun. The problem with them is that their gravity ramps up so steeply. The tidal forces, that's the difference in the pull on your head versus your feet, would stretch you into spaghetti before you even got to the entrance. Lethal. But if you go for a supermassive black hole, one that's millions or even billions of times bigger, well, because it's so huge, the change in gravity at its edge is actually really gentle. You could sail right across its event horizon without a problem. So, yeah, for this trip, we're definitely picking the supermassive option.
All right, we've made our choice, we've survived the fiery approach, and now we're at the main event, crossing the event horizon. This is the part everybody talks about, but what it's really like is way stranger and a whole lot quieter than you'd ever imagine.
And this is super important. The event horizon isn't a thing. It's not a physical surface you can touch or crash into. It's more like a one-way door in the fabric of space-time itself. It's a point of no return, not because there's a wall, but because of causality. Once you're past it, every single possible path you could take leads to the center. Space and time themselves are literally flowing inward faster than light can escape. There's no swimming against that current. And this is where relativity just gets wild. For your friend watching you from a safe distance with a telescope, it would look like you're slowing down as you get closer to the edge. You'd seem to freeze, your image would get redder and dimmer, and then you'd just fade away. It would look like you never actually cross. But for you, in your spaceship, nothing. Absolutely nothing special happens at that moment. No flashing lights, no jolts, no dramatic music. You just sail right across. It's a completely seamless, quiet crossing. And the weirdest part? Both of you are right. It all just depends on your point of view. So while the moment of crossing is, kind of boring, what you're seeing is anything but. The black hole's gravity is bending light so much that your view of the sky just turns into a total Escher print. A star that's behind the black hole might show up in 2, 3, or even more places at once, all stretched into these weird arcs and glowing rings. The entire universe of stars behind you would get squished down into the shrinking little window of light. It would be, without a doubt, the most spectacular and bizarre thing you could possibly witness. Okay, we're in. The connection to the rest of the universe? It's gone. Forever. Inside here, the rules have changed. Space and time have kind of swapped roles. And now, every single path, it doesn't matter which way you point your ship, how hard you fire your rockets, every path leads to one singular inevitable destination. But here's a surprise. The end is an instant. If you're inside a big supermassive black hole, like the one at the center of our galaxy, Sagittarius A star, you could have hours left. A few hours of your own personal time, what physicists call your proper time, to just be there, inside a place from which no information can ever escape. So what happens during those final hours? Well, those tidal forces that were so gentle back at the horizon, now they start to grow, and they grow exponentially. And this is where we get that famous and kind of gruesome term, spaghettification. The pull of gravity on your feet becomes so much stronger than the pull on your head that your body gets stretched longer and longer, while at the same time being squeezed from the sides. Yeah, like spaghetti.
And this process is just absolute. First, your body would feel that strain, and then it would simply be pulled apart. Your ship, no matter what it's made of, would get torn into its component pieces. And as you get closer and closer to that singularity, that point of supposedly infinite density at the very center, the forces become so powerful, they don't just break things apart. They unmake matter itself. They rip apart the very atoms that you, your ship, and everything else is made of.
Okay, wow. Let's pull back from that pretty grim ending for a second. If nobody can ever come back and tell the tale, how in the world can we be so sure about any of this? How do we even study these things that, by definition, we can't see? Well, it turns out we have some absolutely incredible ways to confirm what Einstein's theories predict about the outside of black holes. You've got the LIGO observatories, which can literally feel the ripples in space-time, gravitational waves, when two black holes smash into each other. You've got the Event Horizon Telescope, which took that now iconic picture of the shadow of the black hole in galaxy M87. We can literally track stars, like one called S2, as they whip around the black hole at the center of our own galaxy at insane speeds. And our computer simulations of all this, they match what we observe with just stunning accuracy. So all of this gives us huge confidence that the physics we're using is on the right track. But ultimately, that's where our direct knowledge has to stop. We can check our math for everything happening on the outside, right up to that edge. But what goes on inside, that is, by its very definition, a one-way story. A private story that can never be told to the rest of us. We can write the equations, we can theorize about it, but we can never, ever get the data back. It remains a place beyond our reach, a true boundary to our knowledge of the universe.